Lesson we're going to learn about polynomial functions. So let's get through some terminology first, and then we'll get into some problems. So first, this terminology should not be new. You should be familiar with polynomials from algebra, but let's just go over it. So a polynomial function can be written in the form a sub 0 plus a sub 1x plus a sub 2x squared plus etc. up to a sub n x to the n. Now, let's make some sense of that. It also can be written in different ways. In this case, it's written in ascending power of the variable, but it can be written in descending power too. All these a values, a0, a1, a2, etc., those are going to be constants. Okay, they're going to be numbers. And then you have x, which is the variable for the function, is going to be raised to different powers. So first power, second power, third power, fourth power, fifth power, up to whatever the highest power is. We'll call that the nth power. And sometimes you see it written in ascending order that way in terms of the power. Sometimes you see it written the other way. So say like x cubed plus x squared plus x to the first plus some constant. Okay, maybe you see it that way in descending powers. But the idea is you have x to these positive powers, okay, whole number powers, and then there are constant coefficients in front of each one of those terms, okay? All those a values, like I said, they're called the coefficients. They could be positive, negative, zero. They're whole numbers, decimals, fractions. I mean, basically those constants out in front, those a sub values could be anything. Then we define a term of a polynomial to be any one piece of the sum. So essentially a sub I x to the I, that the a and the x combined, that will be considered a term of the polynomial. So you have the coefficient and the x to some power there. And the degree of the polynomial is based off of the highest power for the variable. So in this case, this would be nth degree polynomial. This one would be a third degree polynomial. Okay. The leading term is the term that contains the highest power. So that would be the coefficient plus the x to the power all together would be considered the leading term. And the coefficient of that term is called the leading coefficient. So if I gave you this function f of x equals 5x to the fourth minus 3x squared plus 1/4 x minus square root of 7. This would be a polynomial. In this polynomial, the degree would be to the fourth degree because that's the highest power. This would be considered the leading term as a whole, and then the 5 would be considered the leading coefficient. Okay? Let's look at polynomial functions in terms of their graphs. They have very distinct characteristics. Two. One characteristic is that they are continuous, which means that there's no gaps or breaks or holes in the graph. And so this right here is all one solid piece. So that would be the depiction of a particular polynomial function, as opposed to this one here, where there is a break right there between the two pieces. That could not depict a polynomial function. Another thing that polynomial functions have in terms of their graph is they are only nice, smooth turns and bends in the graph. There are no sharp turns. It doesn't come to any points. So here, some of the turns might be sharper than others, but still there are smooth turns and bends. As opposed to this right here where you come to a sharp point right there, that would not depict a polynomial function. So smooth turns and bends, all one solid piece, those are the two defining characteristics of a polynomial function's graph. With two of the simplest polynomial functions we can work with, they would be the even and the odd power functions. So a power function would just be a polynomial function that has one term, and that term is x to the n, whatever that power is. And we'll look at that power being even versus being odd. If that power is even, such as x squared or x to the fourth, all those polynomial functions, those power functions, okay, have the same general shape to the graph, and it's this U shape that you would get to the graph. Now notice, that one right there is x to the fourth that I just highlighted. This one, this gray one here, is x squared. Now they do have a different curve to them, the x squared versus the x to the fourth, but they both have that general U shape. The higher the power, the more extreme the curve gets. If you notice in here, we're tucked in closer to the x-axis, and then we get much steeper once we get past that point of an x value of 1. And as the power increases, that will happen more and more and more as we go. But still, we will retain the U shape. And then if we have an odd power function, we have this, what we sometimes call the S curve, okay, here. And notice the gray one versus the black curve, this one, the gray being the x cubed, it's a little more subtle in the cube versus the fifth. But anyway, the gray versus the dark black is the cube versus the fifth power in our odd power. Same idea, the more higher the power, the more extreme this S curve will get, but still will retain that same general shape. The way to get into discussing graphing a polynomial function is to first talk about it in terms of transformations. Transformations are a way of altering the function and then therefore altering the graph of the function accordingly. First one, we'll talk about our translation. So let's look at three functions all related to the squaring function. So we have our basic f of x equals x squared, and that's depicted by this graph right here. Then we have this x minus 2 squared. In this case, we subtracted 2 from the x before we squared it, and that would be depicted by this graph right here. And then the last one is we have the x squared, and then after we square, we add 2 to that square, and that's depicted by this graph right here. Now, the first one is just your basic x squared function. It's got the U shape to it. The vertex of the U is right here at the origin. Okay. Then we have the x minus 2 squared. Now, the x minus 2 is happening before we square it. And notice what happens. Here's the origin right here. We moved 2 units to the right. Okay. So subtracting 2 inside the square moves this 2 units to the right. And then we look at this one here, x squared plus 2. Here we added the 2 after the square. And notice what happens. Here's the vertex, here's the origin, 0, 0, and now we're up 2 units. Up 2 units for our parabola. So where we do the operation before we square or after we square makes a big difference, and what direction it moves is based off of what that operation is. So if we evaluate a function and we subtract some value inside the function, like we did in that last example where we did x minus 2 squared, inside the square, inside the function, we subtracted 2. So if we subtract any value c, that'll be a horizontal shift c units to the right. If we instead added inside the function, and notice these are both happening inside the function, if we added, that would then move it to the left c units. Now look at these next two. Here we have a function, and then outside the function, we're subtracting or adding some value d. Well, that's going to change it vertically, and therefore subtracting d is going to move it down, and adding d is going to move it up. Notice here on the inside, we subtract 2, but we move it to the right. That seems a little counterintuitive of what you might think would happen. You would think, oh, if it's going to move it one way, subtracting 2 should move it to the left, not the right. But in fact, it actually moves it to the right. Okay? So inside the function, it kind of does a little opposite of what you think is going to happen. Outside the function, it operates pretty much as you would think. Minus outside moves it down, plus outside moves it up. So let's look at a few examples. The cube function that we're then going to alter through these translations. And we're going to do a series of shifts, either left, right, or up and down. And so here in this cube, we have two things happening. This first one here. We have a +1 inside the cube, and we have a +1 outside the cube. So what's that going to do? Well, the inside is going to do it horizontal translation. And since it's a plus, it's going to go to the left. And then the +1 outside is going to change it vertically. And again, since it's a plus, it's going to move it up. So if I was to draw the graph of that particular function, I know that the basic x cube has this general shape to it. Okay? Has that S-curve shape to it. It's an odd power function. But then I have to move that to the left 1 unit, and I have to move it up 1 unit. So now I'm going to be there. And so I'll be here at -1 and +1, and then I'll have my S-curve drawn off of that new point there. So that would be the center of my S-curve, moved to the left 1 and up 1, putting me at this point, -1, 1. Now, what should happen is I should be able to verify that this is correct by taking this x value, plugging it in here for x, and making sure that this y value comes out of the function. So if I was to find g of -1, I would get -1 plus 1 cubed plus 1, plugging -1 into that function. And therefore, I would get 0 cubed plus 1, which would give me 1. So -1 does go to 1, which is exactly what this point says should happen. So it's a quick way to verify that I moved it correctly. Let's look at the next one. So in the next one here, we have a -2 inside the cube and a -4 outside the cube. So what are they going to do? Well, the -2 inside is going to move it to the right, much like we saw with the square that had a -2 inside. And then the -4 outside is going to move it down. So again, if I was to graph this function and I know what the basic shape should be, the basic shape should be this cube S-curve shape. And this is not 100% accurate. We're really just getting a rough sketch in here. But I know I should move it 2 to the right, so 1, 2, okay? And then I should go down 4, so 1, 2, 3, 4. And so I would be located at this -4 here, this +2 here. That would be my center point, and then my graph would have to come off of that, like this. And since it's so far down, it's hard to kind of draw that last part, but that's basically where I would be, this point being 2, -4. And if I were to plug 2 into this function, I would get -4 as an answer out. But that would be the new graph. So this is my new graph. This is my new graph for this transformed version of this cube. Another type of transformation that's a little bit more difficult would be the reflections. There are two types of reflections we'll talk about. One is the reflection around the x-axis, and another is reflection on the y-axis. These are dealt with multiplying by a negative. Here, if we multiply by a negative outside of the function, that reflects it in the x-axis. Here, if we multiply by a negative inside the function, it'll reflect it along the y-axis. Now, the idea of that type of reflection is this. If I have something here, okay, and I reflect this along the y-axis, it's going to then place it over here, okay, directly across the y-axis, okay, as a mirror, the y-axis being the mirror. If I have something that's right here and I reflect it along the x-axis, it's going to place it here, okay, reflecting it along this x-axis as the mirror. So, and vice versa, if I start over here, I can reflect reflect along the y-axis over to here. If I start over here, I can reflect along the x-axis and put it over here. Okay? So if you take the entire graph and do that, okay, then you have to make sure that every point reflects in the appropriate manner. But it's all about whether that negative is inside the function, in this case that one is inside the cubed, or outside the cube, or outside the function, as it is in here. This one being inside would be the y-axis. This one being on the outside of the cube would be the x-axis. Reflection. Now, we also, in each case, have a movement. Notice, there is a movement plus 3 outside the cube, which would move the graph up 3 units. Now, the order in which you do your reflections and your translations, your shifts, left, right, up, down, matters. As far as the movement left, right, up, down, that does not matter what order you do those separate steps in. You can go to the right and then up. You could go up and to the right. You end up in the same spot. What matters is the reflection versus the translation. And I have a simple way to remember it. Flip first, move second. Okay? Flip first, move second. Flip first, move second. That should be the order in which you do these two types of transformations. Flip first, move second. So I want to take my basic cube graph here, okay, and I want to, I don't know if you can see that well, let's do a little bit different color, and I want to flip it in the y-axis and move it up 3 units. And I'm going to do the reflection first, then the movement second. So if I flip that over the y-axis, this has to come over here. So now I have this shape. And this has to come over here. So then I'll go like that. And so that's my new graph. So what I'm going to do now is I'm going to erase that old one. Okay? And these little arrows. All right. Now that I'm reflected, what I then want to do is I want to move this up 3 units to here. So that'll be a y value of 3. And so my final graph, I'll use a different color. Let's use purple. Will look like this. And so that would be my new graph for this entire function. Probably best to erase everything else so you're only looking at the final version. And that's it. If we look at this one, this other function here, where I have to flip in the x-axis and then go up, okay? I'm going to start with my basic cube shape, okay? So I have my cube shape that goes like this. I'm going to flip this over the x-axis, which means this is going to have to come down here, like that, and this is going to have to come up there, so like that. I'll get rid of the old graph, so that's my new S-curve. Then I'm going to move that up 3 units, and my new curve, I'll do it in blue, is going to look like that. Centered right here at that y value of 3. And so we erase everything else. There is my new graph. Now you might say, well, these two look exactly the same, right? They look exactly the same. Well, yes, but we got there differently. One by flipping over the y-axis, the other by flipping over the x-axis. Just so happens with this particular shape, flipping over the x or the y-axis results in the same figure because of the symmetry of the S-curve. But that's not always going to occur with every single function you deal with. Okay? So, order matters. Flip first, move second should be your general rule you go by. And sometimes flipping over the x-axis results in the same thing as flipping over the y-axis, but not always. Here's a question worded differently. It doesn't say graph, it says write the equation. Write the equation of the graph for this function x to the fourth that's reflected along the x-axis and moved up 2 units, okay? So if I wanted to write that function out, this function f of x out, I wanted to do two things. I wanted to reflect along the x-axis so that x to the fourth would have to have a negative on the outside, okay? And I wanted to be up 2 units. Sorry, 4 units, 2 units. What did I say? 2 units. I don't know why I wrote a 4. 2 units, okay? And that would be the function that would depict those movements. So here it wanted you to write the equation, so there, it didn't want you to actually graph it. Different wording, asking you to use the same knowledge to answer the question. This type of transformation are what we call non-rigid transformations. All the ones that we've already discussed, horizontal, vertical shifts, as well as reflections, they are all considered to be rigid transformations in that the shape and the curvature of the graph do not change. We just pick that curve up and place it down in a different location. Then there are non-rigid transformations. And what they do is they'll distort the shape of the graph, okay? Not just shift it and reflect it. They will actually change the curvature of the graph. And so I like to simplify it into 2 types of non-rigid transformations. We could get complicated and try and do it in terms of 4, both vertical and horizontal, but I like to do it just in terms of vertical, because in the end, they end up giving you the same thing. So the idea here is, if you took a function and then you altered it by multiplying that function by some constant on the outside, k, whatever that constant multiplied on the outside is, if the absolute value of it is greater than 1, you have what we call a vertical stretch. If the absolute value of that constant is between 0 and 1, you have a vertical shrink. Now, graphically, what does that do? Well, what it does is it will either stretch the graph up vertically, which ultimately will make the graph look skinnier, okay, like that, or it will compress it or shrink it down vertically, which will make it look wider. So I'm going to give you a better set of pictures here of 3 functions that were all altered, either stretched or shrunk vertically, so that you can see the difference better than my hand drawing. 3 functions. The red is your basic x squared. The blue is 5x squared, so I multiplied that by a 5, which is bigger than 1. And then the green is 1/5 x squared, so I multiplied that by a number between 0 and 1. And look at the 3 graphs. So first we have the basic red x squared. That's your simple parabola. But then comparing the blue to the green, the blue is far skinnier parabola. And that happened because we stretched this thing vertically. Think of grabbing these 2 ends and pulling them that way, okay? And what's going to do is it's going to stretch this thing and it's going to make it look skinnier, okay? Then we take the green and we do the opposite. Take these 2 ends and start compressing it down that way. Start pushing down on it. But leave this anchored right here, this vertex right here, leave it anchored at 0. Well, if I start pushing these down this way, okay, compressing it down, it's going to widen out this curve, okay? And so I have a much wider parabola when I multiply by a number between 0 and 1. I have a much skinnier parabola when I multiply by a number bigger than 1. And they're changing the shape of the curve. And so that would be your non-rigid transformation. Multiplying by some constant bigger than 1 or between 0 and 1 will stretch or compress it, therefore making it skinnier or wider. Let's run through this one more time with a few more examples. So I have 3 here. First, f of x equals negative x to the 7th. So we have an odd power, S shape, and then the negative on the outside means we'll flip it over the x-axis, giving us this graph right here. Notice this S shape's a little more extreme. It's flatter in here and a little steeper on the turns. That's because of the 7th power. And it's flipped, though. It's an S going this way because of the negative on the outside. All right, here we have a negative on the outside. We have a plus 2 on the inside, and we have a 4th power. So 4th power tells us the shape. The plus 2 tells us we're going to go to the left, okay? And then the negative on the outside also means we're going to flip it over the x-axis. So remember, flip first, move second. So we take our parabola, we'll flip it over the x-axis, so now it's upside down. So that's why we have this shape. But then we had to move 2 units to the left, putting us right here at -2, and therefore giving us this shape that's upside down like this. And that's because of the reflection, and then 2 units to the left. Finally, we have this one right here, x minus 3 to the 5th plus 4. The -3 on the inside means we're going to move it to the right. Okay, the plus 4 outside means we're going to move it up. There is no reflection. We have a 5th power, so it's an odd power. And so we're going to go 3 to the right, so that would be 3. And then we'll go 4 up, so that'll put us here at that 4 up. That's the center. It's a 5th power, so it's a little more of an extreme S here in this shape, a little bit flatter in the middle. But generally, that's the shape that we're working with, and so that is our graph. So you see, transformations make it very easy to graph these polynomial functions, but only when a polynomial function is in what we call transformation form, okay? Not every polynomial will be in that form. I want to talk a little bit more about zeros of a polynomial function. And these basically relate to our x-intercepts. And we call them zeros because they're where the function will equal 0, essentially using this idea here, that the function will equal 0, which is how you find your x-intercepts. So we also call these zeros or roots of a function. So 2 statements, both are true. A polynomial function, f of x, that has degree n, the following 2 things are true. 1, the graph of f of x has at most n minus 1 turning points. Turning points are all the points where the graph changes from increasing to decreasing and vice versa. So if your graph does this, this right here would be a turning point. This would be a turning point, okay? So you have n minus 1 turning point. So turning points or at most n minus 1 turning points. So if your degree is 7, then you'll have 6, at most 6 turning points. Okay. The next thing here is that the graph of f of x has at most n real zeros, or x-intercepts. So the degree can tell you 2 things. The degree tells you the maximum number of zeros or x-intercepts you'll have, and it'll also tell you the maximum number of turning points, which will always be 1 less than the degree. This idea of finding zeros of a function is extremely important throughout algebra and then into also calculus. Another set of statements that are equivalent as it relates to zeros of a polynomial, okay? These 3 statements are equivalent statements. They all basically mean the same thing. So when you hear the word zeros, roots, x-intercepts, we're really referring to largely the same thing. So here, a, this value a, is a 0 of some function, f of x, okay? So this value a is a 0. That's the same thing as saying x equals a is a solution to the equation f of x equals 0, which is the same thing as saying x minus a is a factor of that function f of x, which is the same thing as saying a comma 0, that point, is the x-intercept for f of x. So all four of these things are exactly the same thing, just saying it in different ways. A value is a zero of the function, x equals a is a solution to the equation where the function equals 0, x minus a is a factor, and a comma 0 is an x-intercept. They're all the same thing. This question, it says find the real zeros or x-intercepts for the graph of this function. So if we set this function equal to 0, we can then do that. So x cubed minus x squared minus x plus 1 equals 0. We would have to solve that equation. And if it's a polynomial equation, largely the way we're going to solve these is by factoring. So we can use some of the things we've learned throughout algebra to factor. In this case, we'll try factor by grouping. Group these, group these. Let's see what happens. We get x squared times x minus 1. Here we need to get another x minus 1. So if I factor out a negative, I would then have x minus 1 here. Well, now they both have an x minus 1 in them. And then I have x squared minus 1 left over. Well, x squared minus 1 can factor even more. So I have x minus 1 times x minus 1 times x plus 1. And now that I have a factor completely, I set each one of my factors equal to 0 using that zero product property you learned in algebra. And I would get x equals 1 and x equals negative 1. Notice this factor and this factor yield the same 0. So this is a repeated 0, while this 0 comes from this factor and only occurred once. We'll talk about that in a little bit. Okay, find the x-intercepts of the graph for this function. Then also find the possible number of turning points. So the degree of this polynomial right here is 6 at the highest power you see. So the degree is 6. So the number of x-intercepts we'll get, the max number of x-intercepts is 6. And the max number of turning points is going to be one less than that, 5. So to answer this question, the maximum number of turning points we could have for this function would be 5. But we still need to find the x-intercepts, and the maximum number we'll get is 6. Maximum number, not necessarily the one we're going to get, but that's the max we're going to get. So how we're going to do it, we're going to set the function equal to 0. So x to the 6th minus 3x to the 4th plus 2x squared equals 0. And we're going to solve. Again, factoring. Factor out an x squared. You're left with x to the 4th minus 3x squared plus 2. Factor that even further. We could say x squared. We'd have to get 2, so minus 2 minus 1. Then insides and outsides would give me minus 2x squared and a minus 1x squared, which would give me that minus 3x squared. So I can see if I factor further, I have x squared minus 2. This x squared minus 1 would be x minus 1, x plus 1. All right, and now I need to start generating my zeros. So set each one of these factors equal to 0. X squared equals 0 would give me x equals 0. X squared minus 2 equals 0 would give me x equals plus and minus the square root of 2. X equals 1, and that would be from the x minus 1 factor, and then x equals negative 1 would be from the x plus 1 factor. So I have how many zeros? 1, 2, 3, 4, 5. I said I was going to get 6 at most. I got 5. In a way, you could say I did get 6 because this 0 here is repeated because the factor is squared. Technically, there's an x and there's another x. This one is x equals 0. This one is x equals 0. So in a way, you could say there's 2 here, 1, 1. That would be 6 total. We don't really need to get into it. We could just say this is a repeated 0. These are all individual zeros. Those would be the x-intercepts for the function. Now we have something that's really important to graphing a polynomial function. And the good news is it's actually really easy to use. It just takes memorization. So it's called the leading coefficient test. So in this leading coefficient test, we're going to look at two things. The degree, which is based off of the highest power we're going to see, and the leading coefficient, which is the coefficient in front of that highest power term. So that's your leading coefficient, that's your degree. And we're going to compare those things. The leading coefficient is either going to be bigger than 0 or less than 0. And the degree is either going to be even or odd. And if we have that combination, we can decide what's going to happen at the ends of the graph. So we have 4 options. 1, 2, 3, 4. And this will only tell me what happens at the end of the graph. Now, this is a visual of what's happening. We're going to have a better way of writing it out, but let's look at it. So for this one, we have negative x to the 4th plus 7x cubed minus 14x minus 9. The highest power is the x to the 4th, so that's my leading term. The leading coefficient is negative 1, and the degree is 4. So my degree is even, that's here. So my leading coefficient is negative, less than 0, it's here. That matches me up with this box right here. Now, what's happening here? Both ends are pointing down. So if you think of your x-axis going horizontally, here's negative infinity on this end, here's positive infinity on that end. So as I go this way towards negative infinity, as x goes to negative infinity, the y value, since this is pointing down, my graph is pointing down, the y value is going to go to negative infinity. And as I move this direction towards this side of the graph, this one's pointing down as well. Okay? So I could say as x goes to positive infinity, y is going to negative infinity. So this box here is basically, this is the best way we can write that. The 2 arrows give you a visual, but this is the way you would properly write it down. Let's look at another one. G of x, 5x to the 5th, 2x to the 3rd, minus 14x squared, 6 plus 6. Highest power term is right here. The leading coefficient is a 5. The degree is a 5. So I have an odd power and a positive greater than 0 coefficient. This is what's going to happen. So again, thinking of your x-axis going horizontal, it says on this end I am down, on this end I am up. So as I move this way, as I move towards the left, which is as x goes to negative infinity, the y is going to go to negative infinity, just like it did on this one. But on the other end, that's not the same thing. On the other end, as x goes to positive infinity, the y is actually going up. So it's also going to positive infinity. So that's how you would write that one down. So now what we want to do is we want to put all these different things together to try and graph a polynomial function that's a little bit more involved than maybe some of the basic translation ones. So these should be the basic steps you follow. First, you want to apply the leading coefficient test that we just learned. Second, you want to locate your intercepts, both your x-intercept by solving for when f of x equals 0, and your y-intercept by plugging 0 in for x and finding what you get. From there, you're going to want to plot a couple of checkpoints, put the graph together, and you're done. So let's look at this. Sketch the graph of f of x equals x cubed minus 2x squared. First, leading coefficient test, okay, LCT. We look at the highest power and the leading coefficient. So we have 1x cubed. This is positive, this is odd. So positive and odd, if you refer to our little table we had, is essentially up and down on either side. So we would say as x goes to negative infinity, y is going to negative infinity, and as x goes to positive infinity, y is going to positive infinity. That's the first thing we do. Second thing we do, intercepts. So the y-intercept, f of 0. F of 0 would give me 0 cubed minus 2 times 0 squared, giving me 0. That's your y-intercept. Then f of x equals 0, which would be x cubed minus 2x squared equals 0, would give me, well, I factor out an x squared, I have x minus 2. That'll give me x equals 0 and x equals 2. This gives me x equals 0. This gives me x equals 2. Those would be my x-intercepts. From there, we're then going to plot what we know, look for some checkpoints to help fill in some of the gaps that are missing, and then we'll complete our graph. Okay, so just look at a couple of things. We said we had an x-intercept of 0 and an x-intercept of 2. So that's 0 and 2. We had a y-intercept of 0, which is actually this exact same point. We know on this end we have to be pointing up. We know on this end we're going to be pointing down. So the only thing we don't know is what's basically going to happen between this x-intercept and this x-intercept. Because generally this graph is going to go down from here. If it comes up, it can't come up any further than the x-axis and pass it, because there would be an x-intercept maybe somewhere over here, but that's not going to happen. It's going to go down. And the same thing kind of on this end, we know it's going to go up. So we just need to know what happens in between. So we need a checkpoint in between. So if you look, there's an x value of 1 here. So if we take that x value of 1, and we plug it into the function, we can see what's going to happen. Well, our function was x cubed, so 1 cubed minus 2 times 1 squared. Just plugging in 1 where there was an x, in which case we're going to get 1 minus 2, so negative 1. So when you plug 1 in, you get negative 1 as an answer, which means you have this point right here, 1, negative 1. So my graph has to go through that point. So it's going to come up to here, turn, and go back again. So that's what my graph will look like. Notice there's a couple of things happening here. Notice this here, where I came up and hit the x-axis and then bounced off and came down. Where here, I crossed through the x-axis. There's a reason for that, and we'll talk about that. It has to do with this idea of the zeros being repeated. We had an x squared, which gave us x equals 0. That was repeated twice. And we had an x minus 2, which gave us x equals 2 as a 0. That one only occurred once. That has something to do with it. We'll talk about that in a second. But just take a note that these two x-intercepts are a little bit different from each other. Okay, so let's look at those repeated zeros. Okay, so in that previous example, sorry, not that example that we just did, but 2 examples back, we had a repeated 0. Okay, and in our last example, 0 was our repeated 0. Okay, and the idea of a repeated 0 is something called multiplicity. So in general, when we're looking at a 0, say x equals 2 or 5 or whatever, is a 0, remember we said that means x minus 2 is a factor. So you could say that the number of factors that give you this 0 is basically the number of times that 0 is repeated, or the multiplicity of that 0. So if the factor that yields a particular 0 is raised to a power, that power is the multiplicity, or the number of times the 0 is repeated. Well, if the number of times that that 0 is repeated is odd, then you're going to cross through the x-axis at that 0. If the number of times that 0 is repeated is even, then you're just going to touch the x-axis at that spot and bounce off. Again, if it's odd, so let's say it was 3, again, you're going to cut through. If it's even, you're going to bounce off. It doesn't matter how high it is. If it's odd, 1, 3, 5, 7, 9, you're going to cut through the x-axis at that x-intercept. Whereas if it's even, you're just going to bounce off the x-axis at that point. And if you were above, you're going to stay above. If you were below, you're going to stay below. Okay? The higher the power, it's still going to bounce off. It doesn't matter. Okay? If it's 4, 6, 8, 10, it doesn't matter. It will just tell you the behavior. It's going to change how it crosses through somewhat in that it'll flatten the graph out a little bit more. So if you look at this one, let's say at this one versus this one, they're both odd. They both cross through the x-axis. But notice how this one just goes straight through. This one, it kind of approaches and flattens out a little bit, then crosses through, then goes up again. The idea that it flattens out is because this odd number got bigger. If it were 5 or 7 or 9, it would flatten out even more before it crosses and then go up. But it would still cross the x-axis is the thing. Same thing with your evens. Use that idea to sketch the graph of this particular function. Now, in this one, if we're going to do that leading coefficient test, this is not multiplied out. It's already factored for us, which makes finding the x-intercepts easier, but the leading coefficient test a little bit harder. So you would have to think of, if I were to multiply all this out, what would the highest power and leading coefficient be? Oftentimes it's pretty easy to do, because here if you multiply this one out, you would have an x squared as your biggest. This one multiplied into that give you an x cubed, and then the coefficient would be out in front, so my leading coefficient would be 2x cubed. So notice I have an odd power and a negative coefficient. So that would put me in this scenario. So as x goes to negative infinity, which is on this end, y is actually going to positive infinity. And as x goes to positive infinity, y would actually be going to negative infinity. And so I put that arrow to say x is going to, this arrow means goes to. Okay. So that's your leading coefficient test. Again, a little harder in factor form, but it'll make the next step easier. So intercepts. So f of 0, I like to do that one first. It's usually the easier one. So negative 2 times 0 plus 3 squared times 0 minus 5. That would give me negative 2 times 9 minus 5 times negative 5, sorry. So that would give me 1090. Okay? So that is my y-intercept. And then f of x equals 0. That would be minus 2 times x plus 3 squared times x minus 5 equals 0. Now this is easy because it's already factored for us. We just set our factors equal to 0. Well, this will give me x equals 5. Notice this factors to the first power. So that has a multiplicity of 1. This would give me x equals negative 3. Notice the power on that is 2. So this is multiplicity. So this is, m u-l-t-i. That's multiplicity of 2. And now this messes people up a lot, but this gives you nothing. Why? Because you're setting these equal to 0. You got 5 because you set x minus 5 equal to 0. And you solved that and you got x equals 5. And you set this equal to 0 and you got negative 3. Well, if you set negative 2 equal to 0, what do you get out of that? Nothing. So you get nothing out of that. You have two zeros. This one occurred twice and has multiplicity 2. This one occurred once. So if we put this together to draw our graph, we should notice that this x-intercept will behave differently than this x-intercept. Here, we bounce off the x-axis. Here, we cut through the x-axis. If we plotted our points, we would have -3, 90 as our y, and 5 as our other x. Now, we would want to do a little bit of checking here because we wouldn't know what the graph looks like yet. I already have the graph in here for you. So what I would typically say is I knew on this end I had to point up. I knew on this end I had to point down. But I really don't know what was going to happen in between. So here to here, here to here. So I would have took a checkpoint, say, I don't know, maybe -1, and found, f of -1 and figured out what the y value is for that. I would have got something right around here. Then I would have took a point or two in here, so maybe f of 2, found out what that equaled. That would give me a y value here, so I would know I would go from here, I have to go up a little bit, and then I start coming back down again. So checkpoints would help me fill in all this stuff that I probably wouldn't know, but what I really wanted to show you on this graph is look at this x-intercept. Look at the fact that this is hitting the x-axis and then bouncing off. Look at this x-intercept. Look that I'm cutting through. This had multiplicity 2. This had multiplicity 1. The behavior is very different.